Let's move on to question 1c. So referring to figure 2, calculate the current flowing through the 5 ohm resistor and the 4 ohm resistor. So you are being given a circuit with multiple sources of EMF. So we are going to solve this question here using Kirchhoff's rule. But the thing is, different students solve questions involving Kirchhoff rules using different method. So some of you might be familiar with using sum of current in equals to sum of current out. Together with the loop rule, which is sum of epsilon equals to sum of IR. So if you are a student which usually solve Kirchhoff's rule using these two equations, then please continue to watch this video. However, if you are being taught to use sum of I is equal to 0 and sum of V is equal to 0 to solve questions involving Kirchhoff rule, then please skip this video and watch the alternative solution video. So it will be the next video in the playlist that you are given, or you can also find the link to this alternative solution video in the description of this video. Okay, so if you are using the first method, which is sum of in equals to sum of out and sum of epsilon equals to sum of IR, then please continue to watch this video. So, referring to figure 2, calculate the current flowing through the 5 ohm resistor and the 4 ohm resistor. So you are being given with a circuit over here which consists of two batteries, or we can call it as two sources of EMF. So one of them is a 12 volt battery, one of them is a 14 volt battery. Then in this circuit also, they have 4 resistors being installed in the circuit, which they name it as R1, R2, R3 and R4. Then they also label the direction of the current on certain portion of the path, which is labeled over here I1, I2 and I3. And now they're interested to find the current flowing through the 5 ohm resistor, which is the current flowing through this portion of the circuit, and the current flowing through the 4 ohm resistor, which is the current flowing through this portion of the circuit. So we are going to solve this problem using Kirchhoff rules because this question here involves multiple sources of EMF, or multiple batteries as we call it. So when you have a circuit involving multiple batteries, you cannot just reduce them using simple series parallel combination. You cannot just do your series merge and your parallel merge together. You cannot do those things. It's not easy to do those, and possibly it can be impossible to do that as well. So to solve that kind of problem, you have to use Kirchhoff law. Okay, so the way that I usually do Kirchhoff's rule, I will follow through a sequence of steps. The first step will be labeling everything. Labeling all components. So when I say I label all components, that means I'll be labeling the electromotive force, the batteries. I will label them using the electromotive force. I'll label all the resistance as well, and I'll label all the current as well. Okay, then once I've done that already, I'll look at whether the current flow is logical or not. Okay, then once I'm done with everything, checking that everything is okay, then I'll move on to do the junction rule and the loop rule. Okay, then once I'm done with both of these rules, then I will move on to solve my equation. Okay, so we are going to follow through this sequence of steps to solve this problem, and we are going to solve it together. So the first step says that we are going to label all components, which includes the electromotive force, the resistance, and the current. So the electromotive force is specifically for batteries. So if you see any batteries, you have to label them, give them names, okay? So in this case, you can see that in the diagram given in the question, they don't give names to the 12 volt battery, they don't give names to the 14 volts battery. So what do? You give them names by labeling them as epsilon 1 to show that this is the battery 1. Then this one is battery 2, you label it by epsilon 2. Okay, so if there's two batteries, then you give them two different names. One is epsilon 1, one is epsilon 2. Then in this circuit diagram, we also have 4 resistors. So you have to make sure every resistor receives a unique name. So you cannot have overlapping, this one called R2, this one called R2 as well. Each of them deserve a unique name. So here you have R1, R2, R3, and R4. So everything is labeled clearly for the battery and the resistor right now. The last thing you need to label is the direction of flow of current. So the direction of flow of current is already being labeled in the question already. They label I1 to be on the left hand side, I3 to be on the right hand side, and I2 is over here. So you're just bringing back the direction of current being labeled in the question. Okay, so we are done with the first step of our problem solving, which is to give names to everything, label them with specific subscript. Okay, next we check whether the current flow is logical or not. To check whether the current flow is logical or not, we'll move on to look at any one of the junction. Okay, in this case, I can look at this junction. This is a junction because you have 3 connecting wires over here. So if you have 3 connecting wires, it's a junction. Here is also a junction because there's 1, 2, 3 connecting wires over here. So you can either look at the junction on top over here, or you can look at the bottom junction over here. Look at one of it should be good enough if you don't make any mistakes in the middle. Okay, so let's look at the first junction over here, which is the one on top. You can see that there's current flowing into the junction, means we're entering a junction, and that current is called I1. And at the same time, you see that there's current flowing out from a junction, it is exiting a junction, and the current are called I3 and I2. So if you want to check whether the current flow is logical or not, you have to make sure that if there's some current entering the junction, there must also be some current exiting the junction. Means by you cannot have current all flowing into one junction. Let's say I2 is flowing into the junction, I3 is flowing into the junction, I1 is flowing into the junction. Then where does the water flow to? If all the waters are flowing in, you don't have a tanki there, you don't have a water tank over there. It's not logical for it to happen. You cannot have accumulation of charge over here. It's just not logical to happen. So that is not logical, and you cannot have current all flowing out as well. So imagine I1 flowing out from a junction, I2 is the same direction, I3 the same direction. If all the current are flowing out from the junction, where do they get the current from? The current is all flowing out. Where do they get the current from? There must be current flowing in the first place, right? So that is not logical as well. So to make sure there's some current flowing into the junction and there's some current flowing out into the junction, then that means that the current flow will be logical. So you can see here I1 is flowing into the junction, I2 and I3 is flowing out of the junction. So that means there's something going in, there's something going out. So that means the current flow is logical. So if we make sure that the current is logical already, what you can do is you can further label the current. So you label it at any point along the circuit so that later it's easier for you to refer which current should you be substituting later. So this one is I3. Okay, for here I2 pass through the resistor, so here should also be I2 as well. Okay, then over here you have I2 and I3 combined. You can see that I2 and I3 are splitted from I1. That means by I1 split into I2 and I3. So if you combine I2 and I3 together, you should get back I1. Because I2 and I3 is originally splitted from I1. So if you combine them back together, you should get back I1. So you can see, you can check whether it's correct or not by following this path over here. I1 is over here. I1 is over here. Then eventually you see that it all makes sense because I1 is the current over here as well. So this portion of the path are all called current 1. This portion of the path are all having current I3, and this portion of the path are all having current I2. And when you reach a junction, only the amount of current changes across the junction. Okay, so you give you make sure everything is logical, then you label them more so that it's easier for you to do your to check whether it's I1, I2, I3 later. Okay, so you're done with the second step. You move on to the third step, which is to do the junction rule and the loop rule. So Kirchhoff rule consists of 2 rules inside. One of it is called the junction rule, and another one is called the loop rule. So junction rule is more related to the current flow at the junction. Okay, and loop rule is more related to the potential difference across a loop. So we'll go through these 2 rules one by one, first by doing the junction rule. Okay, junction rule in Kirchhoff rule says that the sum of current in is equals to the sum of current out. This is what we have been doing just now when we went to check whether the current flow is logical. Okay, so if you think about it, the amount of current flowing into the junction should be equal to the amount of current that is flowing out from a junction. If the current in is greater than the current out, it's not logical. That means by there will be accumulation of charges over here. Means by the charges come in, never come out. Because if you enter 8 charges or 8 charges enter here, 2 charges come out here, 2 charges come out here, then there will be 4 charges left here, right? So we say we cannot have any charge being accumulated at the junction. So that will be illogical if sum of I in is greater than sum of I out. And of course, the opposite cannot be true as well. You cannot have 8 charges coming out, but you only have 2 charges coming in. Then where do you get the 6 other charges from? It doesn't make sense as well. So you have to make sure sum of I in is equal to sum of I out at any junction. Okay. So we are going to pick one of the junction. One of the junction is enough. You don't need to do it for all the junction. Just one junction is enough. In this case, we pick this junction over here. And we can see that the current flowing in is called I1. And the current flowing out is called I2 and I3. So you put I1 to be current in. And you put I2 and I3 on the right hand side because it's current flowing out. There's no negative sign over here. You don't need to check whether the you need to put positive sign or negative sign here. Okay, if it's in, you put on the left hand side. If it's out, you put on the right hand side. Everything is positive here. Okay, so this is the equation that you have. You don't have the value for I1, you don't have the value for I2 and I3 as well. So you are stuck here. If you are stuck here, then just leave it there. Move on to other rule, which is the loop rule. Okay, your aim in this third step over here is to form 3 equations because there are 3 unknowns over here. You have I1, I2, and I3. So aim here is to construct 3 equations. Then you do simultaneous equations to find the 3 unknowns over here. Even though the question only asks for 2 of the unknown, but since there are 3 unknowns, you need 3 equations to solve this problem over here. Now the junction rule has already provided the first equation that you need. Then now you need to find the other 2 equations. Okay, so we move on to another rule, which is called loop rule. Okay, loop rule, many different books provide different definition for loop rule. So in this case, if you follow this method, then it will be sum of epsilon is equals to sum of IR. Okay, so everything regarding to the potential difference across the battery or the sources of EMF, you put it on the left hand side. Everything related to the potential difference across the resistance, you put it on the right hand side. So battery on the left hand side, then resistance, you put it on the right hand side. But for loop rule, you have to be very careful with the sign. So it means by the battery, the EMF of the battery can be positive, can be negative. And for resistance, it's the same thing. The IR here can be positive IR or negative IR. So it depends on the situation. And now we are going to discuss what kind of situation should we put positive, what kind of situation will we put negative. Okay. So there are many ways to solve this problem. So what some lecturers or some books usually do is they will try to label direction on the battery first. Okay, when they try to label a direction, they label the direction where the epsilon will be positive. Means that if your loop follow the direction of the arrow that you're going to draw right now, then it's a positive epsilon. If the loop is going against the direction of the arrow that you draw right now, then it will be a negative epsilon. So what is the arrow that I'm trying to say here? The arrow is like this. If you see a battery, draw an arrow from the negative terminal to the positive terminal. So if I have a battery here, my arrow will be pointing from the negative terminal to the positive terminal. And this is the arrow that I draw. Okay, so what does it mean is later when you check your loop, if your loop is in the same direction as this arrow over here, then you get a positive epsilon. But if your loop is in the opposite direction to the arrow over here, then you get negative epsilon. Okay, that's how some books do it. Okay, so over here you do the same thing for epsilon 2 as well. your arrow should point from the negative terminal, the shorter one, the shorter line, to the positive terminal, which is the longer line. So this is your arrow over here. So later you need to use this arrow to see whether your epsilon is positive or negative. Okay, so once we are done with that thing, then we can proceed to do our loop rule, proceed to construct our loop rule equation. Okay, so what do? We have to see which loop are we going to investigate. So in this circuit over here, there are a few loops that you can choose to study. One loop can be starting from here, going through this path, and ends back at the original position. Okay, a loop is a closed loop, means by you need to start from the one initial position, then go through the external circuit and come back to the same exact starting position. Then that means by you finish the journey of one whole loop. So you need to find what kind of loop is available over here. So you have one choice, which is to start from here, go like this, then come back here. Okay, that means by this small rectangle here, it's one loop. You can also take this rectangle here to be another loop. Means why you can start from here, you can start from anywhere, it's fine. But you have to come back to the initial position. Then you say you complete one loop. Okay, so here I've introduced one loop, which is the left rectangle, another loop, which is the right rectangle, and there's one more loop available, which is the big rectangle over here. So you can start anywhere on this big rectangle and make sure that you go through the whole circuit until you reach back to the same position. Then that will be a complete closed loop. Okay, so for now, I have already decided that I want my loop A to be this left rectangle over here. And since I draw my arrow like this, I'm going to start from here. And I'm going to go through this journey here and end back at the initial position. So I call this loop here to be loop A. So let's try to determine the equation for loop A. So for loop A, we are going to do sum of epsilon is equals to sum of IR. Okay, so let's see what do we have on this loop. So the first thing that we encounter, if we start from here, let's use a highlight pen to indicate where am I pointing. So if we start from here, the first thing that we will encounter, we follow the direction of the loop over here. So the loop here, I draw it to be clockwise. So I'm going to move in the circuit in a clockwise direction. So my highlighter is the direction of the loop. So the first thing that we encounter is the resistance R2. So to determine R2 here will be related to IR over here. It will not be related to the epsilon. Because this is resistance, it will be related to the right hand side of the equation. But to determine whether this is positive IR or negative IR, you have to see whether the direction of the loop, which is the direction of my highlighter, is the same as the direction of the current that I labeled earlier or not. So if you look at this, the current flowing through resistor 2 is I1, and I1 flows from left to right. So what is the direction of my highlighter? My highlighter is also starting to move from left, then move towards right. So that means by my highlighter, which is my loop, is in the same direction as my current. My direction of loop is the same as the direction of current passing through R2. So if it's the same direction, what will happen? We give it positive IR. Same direction, positive IR. Okay. Same direction, positive IR. So in this case over here, the current flowing through is I1. The resistance involved is R2. So it will be positive I1 R2. Okay, so let's continue. We continue our journey of the loop, and the next thing that we will encounter is R3 over here. So since this is R3, its resistance is related to the right hand side of the equation, not the left hand side. The left hand side is only for sources of EMF or battery. So R3 over here is a resistance. To check whether it's a positive IR or a negative IR, again check whether the direction of loop, which is the direction of my highlighter, is the same as the direction of the current that I labeled earlier or not. So the direction of my current is pointing from up to down, and my highlighter is also going from up to down. So that means by my direction of the loop is the same as the direction of the current. If same direction, then it's positive IR. So you have to label as well what is the I. The I is I2, the R is R3. So you have to label them clearly. Okay, so we continue our journey on the loop. Then the next thing that we encounter will be another resistor as well. And this time this is resistor R1. Again, this is resistor is on the right hand side of the equation. So you have I, R on the right hand side. So whether it should be positive or negative, again check. Your direction of your loop, which is the direction of my highlighter, is going from right to left. And the current which is flowing through R1, which is I1, is also flowing from right to left. That means by the direction of current is in the same direction as the direction of loop. So again, it's positive IR. So positive I1, R1. Okay, so we continue on our journey. Then what's left on our journey here? It's the last battery, which is epsilon 1. Again, for epsilon, now this time epsilon, we need to put it on the left-hand side of the equation because left-hand side is for epsilon. So to check whether it's positive epsilon or negative epsilon, again, we see whether my highlighter or my direction of loop is in the same direction as the arrow that I draw earlier or not. If the direction of the arrow and the direction of my loop is in the same direction, positive epsilon. If opposite direction, negative epsilon. So you can see my highlighter here is moving from bottom to top. It's moving upwards. And you can see my arrow is pointing upwards as well. So the direction of my EMF here pointing upwards, the direction of my loop is also pointing upwards, same direction. So you should expect this to be a positive epsilon 1. Okay, so you continue on your journey once you have finished with this. And I believe what's left is the end. You reach back to the original position. So you have completed one loop, and this is the equation that you obtain. Okay, so we are done with this equation. What you can do right now is you can substitute the value, but I'm not going to substitute it first. I'm going to construct the next equation, which is for loop B over here. Okay, so let's move on to discuss how to construct equation for loop B. Okay, so for loop B over here, it's also sum of epsilon is equals to sum of IR. Okay, and I want to mention here, this is for at any loop. Okay, so let's go through the same process like what we did in loop A, but this time I'm going to use another color for my highlighter. I'm going to use orange. So I'm going to start from this corner as well. Then I'm going to move in the direction that I draw for my loop B. Okay, which is clockwise. So now let's go. The first thing that I encounter is R4. Okay, so to check whether it's positive IR or negative IR, I have to see whether my current is in the same direction as my loop or not. My loop or my highlighter is going from left to right. Okay, my highlighter is going from left to right, and my current I3 is also going from left to right. So they are in the same direction. That means it's a positive IR. So positive IR, positive IR, you have to label what is the I, what is the R. So in this case, it's I3, it's R4. Okay, look at the diagram over here. It's I3 in this portion. It's passing through resistor R4. Okay, so let's continue our journey. So we will pass through some connecting wires, and the next thing we encounter will be a battery. So battery, it's a source of EMF, so we will be dealing with the left side of the equation. So now we have determined whether the epsilon deserves a positive sign or a negative sign, whether it's positive epsilon 2 or negative epsilon 2. To do that, we see whether our loop, which is our highlighter here, is it in the same direction as the arrow that we draw earlier. Okay, our loop here is going from top to bottom, so the loop is going downwards here. It's going downwards. I'm not looking at current I3, I'm looking at my highlighter. My highlighter is going down. Okay, but as you can see, my arrow here is going up. So they are in opposite direction. If opposite direction, then it's negative epsilon. Okay, always remember same direction, then it's positive. Opposite direction, then it's negative. Okay, so this one is opposite direction, so it's negative epsilon 2. Okay, so I'm done with this battery. I'll continue to move in my circuit. So I'll pass through some connecting wires. Again, connecting wires. Continue back up. And the next thing that I encounter will be resistor R3. Okay, so resistor is definitely the right hand side of this equation over here. So let's try to determine whether it's positive IR or negative IR. So again, it will be IR, but positive or negative. Again, check the direction of loop. The direction of loop over here will be going from bottom to top. It's moving upwards. My highlighter is moving upwards, but my current at this path over here is flowing downwards. You see that I2 is going downwards, but my highlighter is going upwards. So that means that my direction of loop, which is direction of loop here pointing upwards, is in the opposite direction to the direction of current, which is flowing downwards. If opposite, again, remember it's negative. So over here, this should be negative IR. But what the current flowing through here is I2, and the resistor that you pass through is R3. So I2, R3. Okay, so that's it. And we will be able to reach back to the initial position once again. Okay, so we have completed our journey on loop B. So that's everything that we have for loop B. So let's continue to substitute in our resistance for R1, R2, and R3. Substitute our epsilon 1 and epsilon 2 in order to get an equation that we can use to solve. So I'm going to substitute epsilon 1 is equals to 12, so it's positive 12, and it's equals to positive R2 is the value that I have, so I substitute in R2. R2 is 2I1 plus R3 is the value that I have. R3 is, where is R3? R3 is 6 ohm, so it's 6I2. Then continue. I have R1. R1, where is it? R1 is 5 ohm, so it's plus 5I1. Then after that, what do I do is I arrange the equation in the form that looks like this. I1, I2, I3 is equals to something. I'm going to arrange this in this form, not equals to 0, it can be equals to something. Okay, so if you look over here, the terms that are related to I1 is plus 2 and plus 5. So plus 2I1 plus 5I1 will get plus 7I1. So that means that I1 will have plus 7 in front of it. Okay, continue. Things that are related to I2 is only this term only, so it's plus 6. And lastly, things that are related to I3 in this equation, none of them are related to I3. So I3 is irrelevant over here. We can say plus 0. Okay, then the rest of the thing, we will shift it to the right hand side over here. So that will be just positive 12. Okay, so technically it can be a bit confusing because I flip the whole equation. I bring everything on the right hand side to the left hand side. I bring everything on the left hand side to the right hand side. Okay, but I hope you can check it for yourself. Make sure all the signs are correct. If you got your sign wrong, then yeah, that's where the problem comes in. Okay, so this is done. This is our second equation actually. Right, yes, second equation. And our third equation, we will proceed to do our substitution. So third equation, negative epsilon 2 is 14, so negative 14 is equals to plus IR4. R4 is over here, 4 ohm, so this will be plus 4I3. Then continue, we have negative I2 R3. R3, it's where? R3 is over here, 6. So this is negative 6I2. Okay, be very careful. When you substitute R3, just substitute in the 6 inside. You keep the negative here, so it's negative 6I2. So now again, you arrange the equation in the same form. You have I1, I2, and I3 equals to something. So let's arrange it. You have I1, you have I2, and you have I3, and it's equals to something. Okay, I1, there's no terms related to I1, so you should expect that I1 will be 0, I1. Continue, I2, there's only one term related to I2, and it's negative 6 in front. So I put negative 6. Continue, I3, the only term related, has a +4 in front, so I put +4 in front. Then now I bring the -14 to the right hand side, so it's now -14. Okay, even though I bring it to the other side, I don't change the sign because I'm flipping the whole equation around. Okay, so do make sure your equation is consistent over here. If it's just make sure it's consistent. Okay, don't suddenly this one change to positive but this one still remain as positive, something like that. Make sure everything is consistent. This is just maths. Okay, so before we proceed, I think it's appropriate that we arrange our junction rule in the same form as well. So I'm going to arrange it in terms of I1, I2, I3 equals to something. Okay, so what I'm going to do is I'm going to bring I2 and I3 to the left hand side. So in that case, it will be -1 I2, it will be -1 I3. Again, I bring it to the left hand side, it will be -I2, it will be -I3 if I bring it to the left hand side. So it's considered -1, -1. Probably it might make you confused, so let's remove the 1. Okay, so bring everything to the right hand side already. What's left is 0 on the. You bring everything to the left hand side, so what's left is the 0 on right hand side. Okay, so you have successfully constructed 3 equations, and you can proceed to do the last step, which is to solve your equation. But how I usually solve it, I will usually, let me draw a line over here. I will bring all the equation, arrange them neatly in a set. Okay, so I1 minus I2 minus I3 is equals to 0. Then positive 7i, positive 6i2, plus 0i3 is equals to 12. Then I have 0i1, negative 6i2, plus 4i3 is equals to -14. Okay, why do I arrange it neatly like this? Because it helps me to re-express my 3 equation here in terms of matrices. Okay, I'm not going to use the traditional way like substitution or elimination, solve it one by one, bring this I1 is equals to I2 plus I3, then substitute I2 plus I3 to I1, then solve it one by one. It's too time consuming for us. So what I'm going to do is we are going to use our calculator to solve the problem. But in order to use our calculator to solve the problem, it's best that we re-express these 3 equations in a more intuitive form. And we are going to use something that you learned from your semester 1 maths, which is on matrices. Okay, matrices, you also learn that there's 3 equations. Then you can find I1, I2, I3 as well, right? So we are going to use what you learned in maths. We are going to reshape our equation in the shape of matrices. Okay, so this will be 1, -1, -1. Then where do I get my number? 1, -1, -1. 7, 6, 0. So it's positive 7, positive 6, 0. Continue, 0, -6, 4. 0, -6, 4. Okay, then this slim bracket here is for you to put in I1, I2, I3. Okay, I1, I2, I3. Okay, I hope you remember this from your maths semester 1 because this is this one multiplied by this one plus this one multiplied by this one plus this one multiplied by this one. So you get I1 minus I2 minus I3. Okay, then the right hand side here will just be these values over here. Okay, so once you have arranged your equations to be in matrices form, then the rest is just keying it into the calculator, then you immediately get your answer. So if you're not sure how to do this, right, you can bring out a calculator and do it together with me. So I'm not sure whether the camera can catch it or not. So what you need to do is you need to change the mode of your calculator to the equation mode. So if you on your calculator and press mode, you can shift towards the 5th mode, which is called EQN, which stands for equation. So you press on the number 5, and you are given 4, or probably more, I'm not sure, there are multiple options for you to choose what kind of equations are you going to solve. So for this particular model of calculator, you're going to use the second mode to solve for this equation, because second mode consists of x, y, and z, three unknown. You look at mode 1, mode 3, and mode 4, they are not relevant. You need the mode which has x, y, z, three unknown. In this case, the three unknown is I1, I2, I3, which is x, y, z. So you're going to pick mode 2. Okay, so once you enter 2 into your calculator, you'll be immediately presented with a matrices. And this matrices has 4 column, A, B, C, D. So it's not just 3 column. You can press right, you can see the 4th column. And you can see that there's 3 row, which is called row 1, row 2, row 3. So how do you fill in the rows and columns is, you are going to fill it in like this. This is A, this is B, this is C, this is D, and this is row 1, this is row 2, and this is row 3. So you just fill them in accordingly, and when you fill them all up, you press equal, then you'll be given the answer for X, you'll be given the answer for Y, you'll be given the answer for Z. So the answer for X will be the answer for I1, the answer for Y will be the answer for I2, the answer for Z will be the answer for I3. So I've done my calculation. I'll present you with my answer straight away. Okay, don't worry about losing any marks. It is explicitly stated that you're allowed to solve the problem using scientific calculator. So don't worry feeling that, oh, I didn't do any simultaneous equation. Is it correct or not? It's fine. No problem with it. So if you key into your calculator, I believe you get I1 to be equals to 0.38 ampere. You get I2 to be 1.55 ampere, and you get I3 to be equals to negative 1.17 ampere. So you are immediately being presented with 3 answers straight away. But if you remember, the question is not asking for I1, I2, and I3. They're asking for the current flowing through the 5 ohm resistor and the current flowing through the 4 ohm resistor. So if you investigate the circuit diagram over here, the 5 ohm resistor is over here. So the current flowing through it is called I1. So what you can do is you can state on the side, this is the current flowing through which resistor? The 5 ohm resistor. Okay, don't write R1. Actually, you can write R1. Okay, the R1 is being given in the question, so it's okay to write R1. But for me, I write current flowing through the 5 ohm resistor. Whereas if you look at the 4 ohm resistor, which is over here, the current flowing through it is I3. So you can label beside I3 that this is the current flowing through 4 ohm resistor. Okay, I think this is acceptable. It's very clear what are you trying to say over here. Okay, so this is the way we can solve this question, but let me discuss slightly a little bit about some concept. If you look at the current over here, you can see that I3 over here has a negative answer. So what does it mean when we say the current is negative? Well, current is negative in Kirchhoff rules if you wrongly assume the direction of the current in the beginning. Okay, so in the question, they assume that I3 will be flowing through a resistance 4 from left to right. Then you flow through the battery from the positive terminal to the negative terminal. Then you flow through 2 from right to left at this portion of the circuit over here. This is what the question thinks the current I3 will flow. But from the calculation, you see that I3 is a negative value. That means by our prediction is actually wrong. The direction of the current should actually be in the opposite direction to what we assume for I3. So I3 initially it's going in this direction. We can call it a clockwise direction. I3 is in a clockwise direction, but the negative answer here tells us that this assumption is wrong. what actually happened here is the current is flowing in this direction instead. So I3 is going like this, going like this, going like this, going like this. Then you have to change the arrow here to be pointing in this way. Okay, so now if you look at this junction over here, you can see that the current entering is I1 and I3, and the current exiting the junction is I2. So you have both current coming in from left and right, then they merge together and enter branch 2, okay, which is current I2. So instead of saying that the current flows like this, then split into I2 and I3, now the story is I2 and I3 come together, combine, and enter this branch over here. Okay, so if you encounter this kind of situation where you get negative answer, what you can do is you can redraw the circuit diagram after the whole Kirchhoff rules thing. Don't edit the first diagram that you draw, the first diagram that you analyze. Don't touch anything about it. What you do is you redraw the circuit diagram with the corrected current, corrected direction of current. For those that are negative, you redraw the correct direction. After you calculate everything, at the bottom, you draw a new circuit diagram with the corrected direction of current. Okay, then you can say this is a circuit diagram with the direction of current corrected. Okay, again, I emphasize, don't change the original diagram that you analyze because you affect what the examiner see and what they compare with your circuit diagram. So redraw the new circuit diagram with the corrected direction of current after the calculation over here. Then it'll be more appropriate, clearer for the examiner to see. Okay, so this is how you solve a problem related to Kirchhoff rule, and that's it for this question over here.